Welcome all to lecture 19. So, in this is particularly the part of module 5, that is, so module 5 has been divided into 2 lectures where I will be trying to cover the dynamic testing of pile. As we know, like many of the location where we have problematic soil or soft soil at shallower location, or where the sufficiently strong bearing capacity medium is available at deeper depth. So, we have option to go for pile foundation. But what happened during particularly driving of the pile, it will cause some kind of disturbance in the soil medium. So, the soil properties which we are determined based on in situ investigations will remain same or it may change depending upon the kind of disturbance created during the pile driving. So, as a result of which the resistance offered by the soil medium against external loading, which will govern the bearing capacity of the pile foundation, may change. So, dynamic testing of the pile, I mean there are 2 ways, like you can go for high strain testing, there are you can go for other method which are particularly low strain testing. So, overall the objective of dynamic testing is to ensure whether it is related to the cross section, whether it is related to the length, whether it is related to the bearing capacity, like what are the design parameters you have taken into account, whether the same parameters related to bearing capacity or related to resistance offered, related to cross section, same values have been obtained after you install the pile at the site of the interest. Because if the resistance offered by the soil at the site is different from the resistance you have taken in design consideration, later on it will cause problem in the foundation. It can be because of the bearing capacity failure, it can be because of excessive settlement. So, in order to ensure whatever foundation has been designed considering the certain parameters, same parameters has been obtained, or whatever is the actual parameter, making sure into account that the safety of the overall structure is ensured. So, that all whether it is low strain testing or high strain testing collectively comes under dynamic testing of pile. So, this is, you can call it as lecture 1 under dynamic testing, or you can call, like particularly we will be discussing today, high strain testing of the piles. So, as I mentioned, driving of piles into the soil causes disturbance and thus alter the actual soil structure. So, once there is a change in the soil structure, there might be a possibility that the actual resistance offered by the soil will be significantly different from the resistance offered by the soil as indicated during in situ investigation. Like you go to the particular site of interest, determine the resistance or resistance offered by the soil by means of maybe standard penetration test, cone penetration test as we had discussed earlier, or maybe based on geophysical measurements. But because of the disturbance caused while deriving the pile into the soil, which has changed its soil structure, it might be possible it is offering more different resistance. So, objectives, so the with this change in the soil resistance to the external loading, we have to ensure like what is the characteristic, what is the bearing capacity of actual pile which is erected at the site of the interest. So, with this the dynamic testing of pile, particularly high strain testing, comes with 2 objectives, like actual stresses which are developed particularly during impact load, because we know like pile driving means you have some pile head over which you are providing hammer impact, as a result of which the pile is gently pushed into the ground. So, one is the actual stresses which are developing in the pile cross section should be significantly lower, so that it will not cause any kind of shear failure either in the material of the pile or in the surrounding soil. Second, the skin friction which is developed as a result of different layers which are available along the shaft of the pile, as well as the toe resistance based on whatever is the soil property available at the base of the pile medium, whether they are offering sufficient resistance taking into account your design consideration. So, this will also help in deciding whether the actual pile capacity which is casted in situ, how closely it is matching with your design parameters, how closely it is matching with your design consideration. So, those 2 parameters, one is like stresses should be significantly lesser than the strength of the material which is coming into account, particularly the pile material, and second thing, the pile which is once it is finished installation, whether the toe resistance and skin friction or collectively the actual bearing capacity of the pile has been met at the in situ condition. So, the tests which we are going to discuss today are called as high strain dynamic test. These tests are becoming more and more popular nowadays because in majority of the location, as I mentioned earlier, like the kind of structure we are going, so the amplitude of the load is significantly higher, then maybe lateral loads are also playing a dominant role, particularly because of water waves when we say about flood condition or maybe seismic condition. So, there will be lot of cyclic loads as well. Then, so as a result of which more and more foundation people are going for pile foundation or maybe combination of pile and some other kind of foundation. So, those tests are called as dynamic testing of the pile. The beauty of these tests, like you need not do any test separately, anyway you will be driving your pile into the soil. So, you have to put some sensors. Based on the recording of those sensors, you will be able to understand the in situ characteristics of the pile medium. That will help you in understanding how much the resistance the pile can offer against external loading. Similarly, you have restrike test, which is done to understand the long term performance of the pile. So, you need not do the test on all the piles. Suppose at a particular site if you are installing 50 piles or maybe 100 piles. So, this kind of test, which is to ensure the bearing capacity of the pile foundation as well as to ensure the stresses developed during a hammer impact are not causing actually any kind of failure. So, you can actually select randomly 5 to 10% of total number of piles. So, if there are 50 piles, you can go from anything like 3 to maybe 5 piles or more than that, just giving an example. Similarly, so you can do the test both in driven pile as well as in bored piles. Cast in situ you cannot do the test because there will not be any kind of hammer impact there. The test setup, as I mentioned, like the beauty of this test is you need not go for any external source of loading because anyway you will be driving the pile into the soil. So, hammer impact will be there. So, against the hammer impact, the behavior of the soil or the pile will be detected by means of installing two sensors, generally the two strain sensors and one is acceleration sensor. So, strain sensors will help you in understanding the mostly the resistance offered by the soil, and this acceleration sensors will help you in understanding what is the particle motion at different medium depending upon the intermediate depth or maybe the toe, which whatever is offering more and more resistance to the external loading. So, that is why you have strain sensors more precisely and you have acceleration sensor. So, these sensors which will be maybe piezoelectric sensors and other kind of sensor which will be bolted, not piezoelectric, the other kind of sensors maybe. So, these can be bolted on the periphery of the pile such that the minimum depth should be 1.5 times the diameter of the pile from the top of the pile, that is from the bottom of the pile head, 1.5 meter diameter, 1.5 times diameter you go, and from there onward you can put those sensors. Generally we put the sensors on diagonally opposite end, so that even there is some kind of bending during installation, that kind of bending can also be detected by means of the sensor recording. Of course, you have to take like 1.5 times is the dimension given to take as a reference. You have to also ensure that the sensor should be installed at such a depth that the hammer impact is not going to compromise the safety of those sensors. So, you have to also take into account 1.5 times the diameter as well as the safety of the hammer, because above the hammer there is continuous hammering happening, which is actually driving, as well as it might be possible like it may cause some kind of damage to the sensor. So, you have to make that into account. Now, the sensors, as I mentioned, will be attached diagonally opposite ends in order to also check whether there is some kind of bending while driving the pile. So, as you hammer, the pile will be pushed into the ground and sensors will detect any kind of a resistance offered by the pile medium at different depth. Collectively, the pile medium is resistance finally offered by the soil to the pile, which will be the resistance offered by the pile to the external loading. So, the sensors are detecting these things in terms of analog format, which will be sent to the control unit or PDA unit, in terms of digital signal. The test is known as PDA, Pile Driving Analyzer. So, based on this test you put the sensors and detect how much is the resistance offered by the pile, or which is an indication of how much is the resistance offered by the soil medium against pile driving, because the same resistance will be offered when the pile is loaded to any kind of external loading. Here we have to take into account whether I mean what are the mediums from which the records will be detected, or the disturbance will be detected by the acceleration sensors, or what are the medium which is offering resistance which will be detected by strain sensors. So, that will collectively help you in understanding, just like if this is like toe resistance, if it is provided, then whether it will be detected, it will result in velocity detections, or whether it will help in strain detection. So, accordingly with this fundamental difference, this whether the soil, whether the pile is freestanding pile, whether it is frictional pile. So, accordingly the importance of each of those sensors, whether it is strain sensor, whether it is acceleration sensor, will come into picture, or it is like partially it is skin friction and partly it is by end bearing. So, both the sensors will come into picture, will detect how much is the resistance offered by the pile. So, output we generally get is how much is the load carrying capacity of the pile, or how much is the resistance the pile can offer against external loading, which in this case is hammer impact. Second thing, the stresses which are developed against this impact load, which is particularly the drop of the hammer. What are the stresses developed? Both compression as well as tension, both can be measured. Second thing, any displacement happening while driving, so lateral displacement which is maybe responsible for bending of the pile also. So, that can also be detected once you put the sensors on diagonally opposite ends. Then this is very important thing, like how many number of blows will be considered as for installation guideline in order to terminate further driving of the pile. Otherwise, pile will not go further into the soil, rather there will be crushing of the material. So, that blow count termination guidelines can also be attempted, or can be obtained based on these in situ tests. Then minimum depth of installation, taking into account how much is the resistance the particular pile has to offer against the external loading. So, the minimum depth of installation can also be detected here. The inputs which are required here is pile dimension, what is the length of the pile, what is the cross section of the pile, what is the characteristics of the pile medium like Young's modulus value and so on. Then hammer details, what kind of hammer you are using for actually driving it, hammer efficiency also comes into picture. Then what is the weight you are dropping, what is the height from which you are dropping, that will govern your impact load magnitude. Subsoil information, so depending upon the subsoil information, whether the pile has to be designed as skin friction pile or end bearing pile, or a combination of those will come into existence. So, generally this subsoil information you will get from bore log data. Then any other information, to give you an example like hammer impact efficiency, or some kind like problematic soil is there, some collapsible soil is there, water table depth, other thing which can actually affect the your field recording can also be taken into account as possible input for analysis. Now, interpretation, as I mentioned, so strain sensors will help in detecting how much is the force applied or impact load or the resistance offered by the soil, whether it is skin friction, whether it is end bearing. So, what is the resistance offered by the soil at different layers. Then acceleration sensors will detect the propagation velocity, because you are actually causing some kind of disturbance, as a result of which there will be some kind of particle movement within the hammer material. So, that will be detected by acceleration sensors. So, this has to be clear, otherwise it will be difficult to understand what is the role of strain sensors, what is the role of acceleration sensors. So, very clearly, like strain sensors will be used to find out the resistance to impact load, acceleration sensors will be used to find out the resistance offered by the pile material, maybe in the form of propagation velocity, particle velocity. This should be like propagation velocity of pile material, of particles against hammer impact through pile material. Solution if arrive based on wave propagation as well as interpretation. So, depending upon the nature of the resistance provided to the pile, sensors will detect direct wave as well as reflected wave. So, it is like there is a pile, maybe next slide I am going to discuss like what is the meaning of direct wave as well as reflected wave, based on which the sensor will be detecting like strain sensor will be detecting the force component, acceleration sensors will be detecting corresponding velocity components. Some will be from direct, some will be from reflected. So, depending upon whether it is a whether the medium is offering some resistance, then reflection will be in which parameter, or whether the medium is not offering any resistance, then reflection will be of what parameter. So, we are going to see that thing in coming slide. Rossi in 1985 actually provided the solution in case of pile subjected to hammer load. So, in this particular case the impact load is hammering, or the top of the pile which is actually causing the impact load, that will be so Rossi in 1985 Rossi et al. Provided the solution for this. So, what we are interested, first of all, as per Timoshenko, et al. 1970 provided the velocity of particle motion, against impact load through a rod. As so velocity of propagation of velocity of particle movement is given as c over EA f t. So, where c is propagation velocity through the rod medium, propagation velocity of wave. So, one is propagation velocity of wave, second is the velocity with which particle movement is happening as a result of passage of wave, propagation velocity through pile medium, which will be as discussed in geophysical test, which will be depending upon the characteristics of pile material. So, which is Young's modulus, E is Young's modulus and rho is mass density of medium now A is cross section area of pile, Ft is force or impact load, which is generally considered as positive in downward direction and negative in upward direction. Now, this is given like you have some infinite rod and you have some rod and you just provided some impact load. As a result of this impact load, wave will be propagating and this wave depending upon the characteristic of a particular wave will cause particle motion. So, if we discuss like P wave, S wave, so depending upon the wave the particle motion will be varying from one to other. Like, so in this particular case what we are doing is we have some pile. So, this is your pile which is actually you are driving into this. So, you will having some kind of pile head, and on this you are actually putting some kind of hammer impact. Now, as a result of this hammer impact, what will happen? There will be shock wave generated here and will start traveling downward. So, what we are detecting? We are putting some maybe acceleration sensors, same way we will be detecting some strain sensors as well. Strain sensors, acceleration sensor. Now, what will happen? So, this one the equation 1 which I told you, this is like you created some kind of impact, as a result of which this disturbance will be created and will be going downward. So, this is like first component. It is like I have created some kind of disturbance, as a result of which this acceleration sensor detects the disturbance which is given by equation 1. Now, what is happening in this case, particularly in case of again, so in case of very low damping, stresses will be same independent of time and location of observation and location of observation. Now, what happened? This is, as I am repeatedly telling, this is particularly the case where you are having a rod, you provided some impact load and simply the wave propagated through it. What happened in case of, like suppose in case of, I am telling here like case 1, in case of freestanding pile, so being a freestanding pile, what will happen? You actually initiated or triggered some kind of disturbance at the pile head, as a result of which this disturbance, first it will be detected by the acceleration sensor. So, there will be some kind of disturbance here which you can call it as acceleration time history. Now, again this will be going till the bottom, and again there will be strain sensors also. So, that will be detecting your equivalent force or impact load. Now, this reaches a particular depth and then again start traveling, because there will be some kind of reflection from here. Being a freestanding pile, there will be some reflection in case of strain values. So, there will be again some kind of disturbance. Now, considering the length of the pile to be L and the velocity of propagation through earth pile medium as C. So, minimum reflection, the minimum time which will be required by the impact load to get reflect from the bottom will be L by C from the bottom. So, this will be after L by C at this instance, I mean at that toe, but by the time it reaches the acceleration sensor, so it will become 2 L by C, because L one is downward, then another L upward. So, it will be like 2 L by C delay with respect to the direct load or the first recording. So, that you call it as Vt. If I am calling, so that will be called as C over Ea. So, first is Ft I am calling it as again as freestanding, so I am just putting as suffix O, okay, Ft plus more components will be there, strain sensors F. So, second disturbance will be like this reflected, it will reach here while upward component, then after that once it reach the pile head again it will be there will be some reflection from there. So, that will be called as T minus 2 L by C, because L length it took I mean L by C it took from reflecting from bottom, and again by reaching the pile head or the strain sensor again it took an additional time L by C. So, that is 2 L by C. Now, this will be like delayed by how many? So, this will be like one will be component which is coming from downward, that is F, same time almost with no significant change in the time, there will be another component which will be equal to this, but will be reflected component. So, you will have 2 F, this is coming from first reflection. Same way you can have another. So, the reflected wave, first reflection, what will do? It will again just like your actual hammer impact, it will again start travelling downward, and again there will be some kind of second reflection. So, again second reflection will be T minus 4 L by C, because 2 L by C was the actual starting of that reflection from pile head, and then came to the toe and then again reflected back. So, it is like 2 plus 2 4 L by C, and then again it will be twice F. So, one is like directly coming from the bottom, and second one is like reflected from the top surface, because the top surface is fixed one. So, you can call it the pile head is fixed, causing reflection in okay. So, that is like reflection from this thing. Now, this is particularly the case. So, you have some kind of this is like direct impact component as detected by the strain sensor, then you are having first reflection, then you are having plus some more component will be there. So, this is like second reflection. Plus so many will be there, but note we can put here signal after second reflection will be very low, will be very weak to be detected. So, this is like what I can say, like the reflection which is coming from freestanding freestanding pile is like this. So, you are having the base which is causing some kind of reflection in the wave, and then the pile head which is again not allowed to go for any kind of motion. So, which is again causing reflection. So, as a result of which we had considered for our analysis like two reflections. One is impact load, first reflection, then went to the pile head, then again came back second reflection, and after that it will be considered as too weak to be considered into analysis or interpretation part. Now, this is a very simple case where we are having a freestanding pile. Now, what will happen if you are having, so the solution to this equation, the previous equation I should number it as equation number 2. So, the solution to this equation, solution to equation 2 is called as free pile solution. This is a one particular case, free pile solution. Now, case 2 can be, we consider here like freestanding pile, there is no resistance from the sides. What additional complication can be brought here? It is like even the layers at intermediate depths are offering resistance. So, I can say like case 2, in case of skin friction. Now, for simplicity, we are not considering skin friction to be offered by all the layers along which are available along the shaft, but I am considering in case skin friction is offered by an intermediate layer along pile shaft at a distance x from the top, x from pile head. Now, in this particular case what will happen? So, you had just now we discussed about freestanding pile. Now, in addition to freestanding pile, suppose this is the location which is at a distance x. What will happen? You created some disturbance, traveled back and reflected as we discussed in 1, but what will happen if at distance x, this is L, at distance x, it is offering the soil is offering resistance, soil resistance. So, in addition to your toe, even the intermediate some layer is there. Suppose maybe you can consider maybe soil type 1, offering some resistance. As a result of this, what will happen? From the intermediate depth itself, you will be having some kind of reflection travelling upward, half component of that, and some kind of component which will be travelling downward. Upward component is actually causing some kind of compression. So, you will be having, you can say like this will offer resistance from intermediate depth x after time x by c from impact load. So, again there will be resistance offered, will have two components. So, it will have two components here, resistance will have two components, First one, upward travelling compression wave which will be called as Vt C over 1 by 2 C over Ea RT. I am considering the resistance offered as RT at this particular location. Half will be, because half will travel upward while other half will travel downward. So, one is like upward, this is first component, and second component will be downward component traveling tensile wave, but what will happen once it reaches the bottom, like this component, if I am calling it as T, this as C. So, this component once it reaches the bottom, again it will reflect back and travel like a compression wave. So, travel because your sensors, acceleration or strain sensors are here. So, whatever, whether it is coming as direct from as compression wave or the tensile wave after reflection to compression wave will be detected only at this particular location where sensors are there. So, the other one will be Vt, but at a time which will be detected after time, tensile wave which will be detected by sensor after how much time. So, it will be like L, which is the total length it has to travel, plus what is the additional thing is like L minus x over C. So, L is that length by which like L minus x is the length to which it has to travel downward and then reflected back onto the surface by the sensor. So, it will be L minus x, that will be equal to x I am keeping, considering I number of layers are there, I numbers of layers offering resistance. So, that is Lxi. Now, if you consider, so this is like as a result of this unconformity, as a result of this layer which is capable of offering resistance, there will be some component again traveling upward, there will be some component which is traveling downward, but before getting detected at the receiver, it will be reflected from the base or toe and getting detected. So, it will be like this, you can call it as 2L minus Xi over C from hammer impact. So, this is like duration after which the wave which was traveling downward will be detected by the this sensor. The first one will be definitely like T minus Xi by C delay from hammer impact. So, this is like the time of delay with respect to the hammer impact, the one which is detected by the compression or which will be traveling upward, and the second one which will be traveling downward and then after reflection will be going upward. So, the first one will be causing compression and the second one after reflection will be causing compression. So, we can call it as, so change in particle velocity by upward traveling waves from resistance RT IRT will be summation of compression wave velocity directly from the resistance and the waves and other waves precisely tensile which after reflection will travel upward. So, this component which is called as Vt u t is given as C over Ea Ri L t minus twice x I over C plus L t minus twice L plus twice x I over C plus L t minus twice L, it should be 4L plus twice x I over C plus so on, which is not considered because it will be like third reflection, it will be too weak. So, this is from upward component, particularly from the resistance at xi distance. Okay, this should be xi like capital X. So, I am just writing as capital X. Then from downward travelling wave, it will be called as Vt d, that will be equals to C over Ea Ri H minus L t minus twice L over C plus L t minus 4L over C plus and so on, third component which will not be considered here. So, the net velocity change, net velocity will be the summation of upward and downward components which is given as, so the downward component is considered as the upward component is considered as negative, downward component is considered as positive. So, net will be equals to V t t, which will be equal to, last we had given equation number maybe 3, so that I am calling it as equation number B. So, that will be considered as A plus B, which will be equal to C over Ea F t plus 2 times summation j equals to 1 to m F t t minus j times twice L over C minus summation I equals to 1 to n R I L t minus twice x I over C plus summation j equals to 1 to m L t minus twice x I plus twice j L over C plus summation j equals to 1 to m L T minus j to L over C, where m equals to number of impacts and n equals to number of intermediate layers offering resistance to impact load. In this way, if the value of V at time t and V at time t plus 2L by C is known, it will give total resistance as RT, which is given as half Ft plus Ft T minus 2L by C plus EA by C Vm plus Vm T minus 2L by C or which can further be written as F T plus F T minus 2L by C plus M, okay, let it be like this. What collectively I want to say here, like if you know the equation number C, recording force and velocity values at n different times, so you will get the value of F and you get the value of V using equation C will give n simultaneous equations. Okay, maybe n we have used earlier, so I can write it here at p different time will give you p simultaneous equations the values of F t in general and V t in general can be determined from strain and velocity and acceleration sensors the recording has to be done till 4L by C from the impact. Based on this, so using equation for known values of F t, V t up to 4L by C, use equation C and you will be able to determine the value of R t. Using equation C, equation C for known values of Ft again in general and Vt in general. So, this equation is like generalized one, whether if you are having resistance from intermediate depth, it will take into account, because the second component is actually taken into account the resistance from intermediate depth, and if you are not having, only toe resistance is there, then the reflection from intermediate depth component will not be there. So, for known values of Vt and Ft and Vt, equation C can give the value of resistance offered by pile against hammer impact. So, this way, based on the resistance or based on the response of the pile, or more precisely the resistance offered by the soil layer, which is available at different depths, collecting the resistance or the signature against the shock wave, you will be able to determine the value of RT at that particular depth, or collectively the value of R summing over 4L by C duration. So, that is like this is how you can get an idea about the total resistance, because that was the objective. So, this way you can actually get an idea how much is the resistance offered by the pile while deriving, which may be equal or which may not be equal to the resistance for considering the C5 value of the soil obtained from bore log. So, this way you can actually determine how much is the actual resistance the pile in its in situ condition can offer, because if you allow the soil to regain the strength, or by leaving the pile for some more time to regain the strength, so that resistance mostly will be higher than the resistance you are getting from this. But this is going to give you the minimum bearing capacity of the pile against the impact load, and this resistance you can also compare with the in situ strength of the soil, and but precisely the pile material, in order to ensure there should not be any kind of failure in the pile material because of the impact load. So, this is about the high strain dynamic testing, which is done precisely to understand the stress developed and also the resistance the pile medium can offer to external loading. So, same way in the next class, which is lecture 20, we will be discussing about low strain test, which can help you in understanding the integrity of the pile with respect to the depth, the cross section as well as the length, which has been achieved after the pile is placed in its in situ condition. So, we will discuss that in maybe coming lecture. I hope the today's discussion is more clear to you. This discussion is a new one and has not been considered in many of the textbooks. So, try to go through this derivation, try to sketch the diagrams yourself, so that you will get more understanding about the direct component of shock, the reflected component of the shock, which will be detected by the sensors, because so far we knew like some shock is there and you put some sensor, it is detecting, but why it is detecting, from what interface the reflection is coming into picture. So I hope this will be much useful to each of you. Thank you so much.